This is what we're studying with this experiment. The magnetic force on a current carrying segment of wire with length L is given by this formula here, which is current times the cross product of the length of the wire segment and the magnetic field direction. So, but part one, we're going to make sure, first of all, that the magnetic field and the current carrying wire are at right angles to each other. So we're going to be dealing with the sine of 90 degrees, which of course is 1. And so if we make this 1, then this formula here becomes simply current times magnetic field times B, if these two are perpendicular vectors, which we're going to make them to be. So if we divide through by the current and then divide through by the length of the wire, we get the magnetic field. And we did a quick and dirty experiment where you will be taking more data points, twice as many data points, but we took some data points from 0.1, 2, 3, 4, and 5, 1, 2, 3, 4, and 5 amps. You'll be going every half amp. We did it every, just for the demonstration purposes, we did it every 1 amp. And here's the result we got. So the slope of this graph, which is this, and then taking that number and dividing it by 84 millimeters, that's 0.084 meters, we got this value here. So this is the value of the magnetic field, and this is the error in that value, which is just about exactly 1%. So in our half as accurate as yours experiment is going to be, we got a 1% accurate value for the magnetic field. Of course, that's in Tesla. That's 0.08 or 800ths of a Tesla, which is actually a pretty decent sized field. Much bigger than the average refrigerator magnet. Okay, so that's part one. And part two, we also did a cut down version of the lab by going every 20 degrees instead of 10 degrees from 0 to 90 degrees, 10, 30, 50, 70, and 90. And the results we got were that these data follow a sine curve, and the coefficient of correlation was something like 0.9995, and if that were exactly 1, that would be a perfect fit. So the verification here is in your correlation coefficient, which is the closer to 1 it is, the more you've shown that your data indeed fit a curve like this. What we're doing here is we're actually changing the angle between the wire segment, which is the bottom of the wire segment that you see when you look at the video, and the magnetic field. And showing that if everything else is constant, we're keeping the current constant, the length of the wire is constant, the magnetic field is constant. The only variable here is the angle between the current and the magnetic field, and that is a sinusoidal function. So that's the result we got by doing this more rapid, less accurate experiment. Okay, so this is the setup for the first part, where the goal is to measure the magnetic field strength, and it's going to be a good fraction of a Tesla. I think you'll see we got about 0.08 Tesla for our answer. So anyway, here's the setup. This is the constant current, constant voltage power supply. I've got an extra meter here, one of your digital meters, which has another significant figure above the display on the panel here. So we can do a more accurate measurement of the current. So we're going to vary the current, and that's going to vary the force. So we have a wire. At the bottom of this wire is the only wire we're interested in. It's 42 millimeters long, 84 millimeters long, sorry. It's 84 millimeters long, and the current's going either in that direction or this direction. We'll just say it's going that direction. If it's in a magnetic field pointing one way or the other, we'll say the magnetic field is pointing this way, the current's pointing that way, and therefore the force on that current segment is down. The current segment can't go anyplace, but the magnet can, and so it's repelled downward instead of the current segment itself. So that will change the reading on the balance. So if I turn the power on, it's I've got this set at a 1/2 amp, which is your first measurement. You'll see that that indeed it forces it down, and so I had my directions backwards. I just made a guess and got the wrong answer. So the force is down, and then you've got to add additional weight to get it to balance on the balance. So that's the experiment. It's pretty simple. You have to have a nice thing. Paper clips comes in handy instead of your fingers seem to be somewhat more awkward. You can adjust this more finely without bumping it too much with a paper clip or an end of your pencil or something like that. And so we'll do this for every 1/2 amp all the way up to 5 amps. And then do a graph of force, which is the mass difference here converted to newtons, versus current. Okay, so this is the second part of the lab with the goniometer in place. And again, don't put the goniometer in place unless you have your instructor help you with this little wedge to remove the horizontal wire segment from part 1. So we'll take that out very carefully and then replace that wire segment by this goniometer. The goniometer on the bottom has a vertical wire series of wire loops, and if you think about the right-hand rule, if you have a magnetic field going, say, this way and a current going that way, like up or down, the force on that is horizontal, whether the current's going up or down. If it's going down, then the force is horizontal in the other direction. In other words, the scale doesn't measure that force because it only measures vertical forces. So the only thing that we're actually measuring is the magnetic force on the bottom segment of the wires down there, which is not very much. So this is a little bit finer measurement here, and we'll set this at 3 amps, and it stays at 3 amps for the whole experiment. So what we're doing here is changing the angle between, right now it's pointing this way on this setup so we can avoid bumping into the scale pan. So it's set at an angle this way, and the bottom wires are pointing in the same direction as the magnetic field, basically, when this is set on 0, which it is now. And so that means the sine of 0 degrees is 0. That is, it's F I L cross B, or FIB sine of the angle between I and B, the current and the magnetic field, and that's 0. So there's no magnetic force on that. When I turn this angle to some angle, you'll see that the balance changes because there's a magnetic force at a non-zero angle. And so the goniometer goes from 90 degrees one way to 90 degrees the other way. I call it left and right, however you want to describe it. And so we're going to increment this by 10-degree increments to the left and then to the right. And there's a table in your handout for putting data in. And we'll measure the force. We'll balance the balance at 10, 20, 30, all the way up to 90 degrees to the left, and then back 10 through 90 degrees to the right. So we get 18 data points. And again, the idea is to convert that mass difference in grams to kilograms and then to newtons. So there's the vertical force, which is on the bottom wire segment here, and it's a smaller force because the wire segment's a lot less long than the one you did in part 1. And then we're going to graph it and take a look at the results, which we'll show you on the screen. And this will give us data which you want to fit a sine curve, and the formula that you need to put in on the defined function box on the Logger Pro graphical analysis has a 57.3 in the denominator, which is the factor to convert from degrees to radians. So you put in the degrees and the formula converts it to radians for you. So it's the sine of so many radians as it should be. So the fit then, there's not a good fancy way to compare your data, which should fit its sine curve, to a sine curve. So we're going to plot that data, we're going to put in that formula and compare the two by looking at the coefficient of correlation, which is going to be hopefully very close to 1, which means, yes, these data fit a sine curve. And so the conclusion is, we hope, that you will get a sinusoidal, a fourth of a sine curve from 0 to 90 degrees. This substantiates the fact that the sine of the angle between the current direction and the magnetic field is a factor in this cross product. Okay.